sure if that's correct. I don't think it is. Well, that's valves, right? Yeah, okay. Now, most of this is so we kind of skipped over this. We went through directional control valves, but we didn't get to the pressure control valves. Pressure control, starting and stopping compressor, unloading compressor, pressure regulating valves, safety valves, and release valves. And that's what all falls into this. I think so. Pressure relief. What do we mean by pressure relief? What's the difference between a pressure relief valve, a pressure regulating valve, and a safety valve? Above a certain pressure, right? You know what I'm saying? So it opens at a preset and exhaust until the pressure drops. But that's the safety valve. Pressure opens proportionally to the pressure. Must be sized large enough to discharge more air than the compressor can supply. And this is also true, especially pressure regulators. We have people that don't understand that. Your pressure regulators have to regulate below minimum pressure available from the compressor, right? You understand that? Does that make sense? So if my compressor only puts out 60 psi and I set my regulator at 70 psi, it's not going to do any good. You understand what I'm saying? Because how can it regulate something that it's not available to? It's just like on voltage regulators, like on this computer right here, this power supply. Well, to regulate a voltage, you get a constant voltage out when you got a very voltage in. The voltage you have in has to be more than the voltage you get out because we got to regulate below it, right? You understand what I'm saying? So a safety valve opens at a preset pressure and exhausts until the pressure drops below a preset value. So safety valves are in there to keep things from blowing up. Like on the water heater. So you got a safety relief valve on the water heater, whether it's electric or whether it's gas, right? You understand? Because if you don't have something in there that gets when that thing gets over pressure, it could explode. Yeah. A relief valve opens proportional to pressure. So we'll look at this. Hydraulics. This talks about air, but hydraulics usually use a relief valve to regulate pressure. So what they do is anything above a certain pressure, it's going to be back in time. So in hydraulic systems, the pressure relief valve acts like a regulator. And then a pressure regulator, this is the guy that we have over there, reduces the pressure to a level that is safe for equipment to operate. And that's true, but it's also when you go out and buy any type of pneumatic equipment or actuators, it's going to give you the pressure that it's designed to operate at. And if you operate it above that pressure, then what could happen? It could blow out seals, it could mess it up, or it's going to reduce the life expectancy of the device. So it says safety, but it might not actually be a safety concern. It might be a concern where you're going to mess things up. Just like people running speakers higher wattage than what they're designed for, or anything like that. So a poppet relief valve. So these are pressure relief valves. Now what they are is they're pilot operated, right? You understand that? So they actually sense the inlet pressure to determine when they open and when they close. Poppet, adjustable diaphragm. So most of these, some of these pressure relief valve and pressure regulator valves are pre-adjustable. And I'm sorry, that's one of the things I need to make sure I put on my list to show y'all how to adjust one on our pressure regulator on our system over there. Because some of y'all didn't do that. Pressure regulator. So this is what we have. We have a pressure regulator. And most things we'll find out that has the ability to turn in industry. We put something next something that we can't accidentally turn it, or if we do accidentally bump it, we're not going to change something, right? So on our pressure regulator over there, what do we have to do to adjust it? Pull it up. See, that's something I didn't tell y'all. So we pull it up, we turn it, and what's the last thing you're supposed to do is lock it back down. And then you can't accidentally touch it or something like that. We'll look at our flow control valves. Our flow control valves, this is very popular too, where they have a lock. If it's got a thread on it, they'll have a lock nut on it. You tighten the lock nut down, it prevents it from accidentally being adjusted. So when we look at our flow control valves, we'll have that. Regulates the output pressure, automatically closes when the pressure gets too high. And I should put a note in here that your inlet pressure has to be what? I mean, it is set. It's always set below what? The minimum inlet pressure. Now, understand that, sir? Yes or no? We're okay. Fine, can you leave? Diaphragm pressure regulators. This is the symbol for a pressure regulator. And if it's variable, it's got a what on it? Well, no. The spring is what's causing it. So it can open it up, but it's got to have something to push it back down, right? So just about all your regulators and relief valves have a spring. It's just if you got a safety valve on your compressor, and you want to drain the compressor, you have to pull it out, right? You understand? It's got a spring in there that when it drops below the low pressure, it will pop it back in. How do I know it's variable? Because of the arrow. The arrow indicates that it's variable, right? You understand that? And this is usually a dash line. In fact, this probably is a dash line. It's just that it got, when I copied it, it got, or downloaded, which means it's pilot operated. So it actually gets a feedback into it to determine. Precision control regulator manual. I think we got some of these over there for hydraulic systems. Oh, there the dash line really looks good. Now we don't, honest to goodness, in this class, we don't really need to understand the differences between the different pressure regulators. What we need to do is understand the symbol for it, right? You understand it. And we need to we need to know how to adjust them and how they basically work. Well, we don't even know how they work, right? It's just like if I say, how does the cruise control in your car work? You need to know that. No. All you need to know is how to do what? Yeah, how to operate. So the symbol for the pressure regulator is this guy here on the left. Are we okay? And these are all figures probably out of the book. Of course, really, it says it's figure 3.5. Yeah, that's what it says. I got my book up here. I didn't go through the book.
Page 38.
Huh? Oh no, what I've done is I've came back here and I've cut these symbols.
Okay, that's what
yeah. Okay.
I'm talking.
Yeah.
Yeah.
Yeah. Now there's a thing up there in that in course content under reference material that you got all these symbols. Now you have to understand that anything that I can turn or anything that I can push, manually push, and I can manually turn, we can come up with some way to control that electrically, right? You understand that? So these could actually be remotely operated. You could bring in a programmable controller, which is a computer that runs, that you can run machines.
I know most of it, but just for understanding, we say anything I can turn, anything I can do. We still talking about using that same, vehicle on the work to do it, or we talking about a modification?
No, we would have to, we'd have to come up with some way to replace the knob. So it would be a different unit.
Right. That's what
a lot of automated control, a lot of things that are automatically controlled usually have a way to manually override. I mean, that would be awful, my system is not regulated correctly, and I can't adjust it with my PLC or something like that. It's just like on our, I think I showed y'all, these valves right here. So when you look at the side, see that little brass buttons, and you can take like a small Phillips screwdriver or something, you can push that in. You can manually override that valve, even if the solenoid don't work. Because if something happens and one of the solenoids burn up, and you got to do something, you got to do it, right? So even the relays that we use to control motors have a button on it that we can manually override. And I think I brought this up last class. Anytime you manually override something, you need to understand the consequences of what you're going to do, right? You know what I'm saying? There's been quite a few people killed by manual override. People know that they can do it and go ahead and push that thing in. And I think I told you about the guy on number 8 blast furnace. Huh? No, the thing come up and cut it in two. From what I understand, I wasn't over there, but from what I understand, they brought it down to 2 feet. I mean, this was a big door, and hydraulics, hydraulics, you don't fool around with that stuff, right? These guys have extremely high force multiplication. And they locked out everything on the bottom hopper and went down there and the guy pushed in the relay that controlled the solenoid valve and brought up the bottom door, hopper door.
Where on that solenoid do you know that it's manual versus automatic?
Well, this right here, this indicates that it's variable. This symbol right here, I'd have to look it up and see. We'd have to look up an automatically controlled valve and see if there's a different symbol. I'm sure there is. There has to be. But anytime we see this symbol right here, this usually means manually the arrow. And this is true even electronically. I mean, I could put the symbol for a DC power supply, and I put an arrow through it, and it means it's what? It means it's manually adjusted. Resistors, we have variable resistors that have the same symbol. So this symbol is pretty standard over quite a few different fields. So that means the thing is manually adjustable. I mean, that's a good question. I don't know. I just know I've seen voltage, I've seen pressure regulators, I've seen, of course, directional control valves. We know the symbol that we put for a solenoid, right? It's that regulator valve, relief port. I don't know if we got any diagrams in here or not, but and this is what we need. Another thing we need to understand is this service unit. Some people call this thing different things. This is just the unit I picked up. No, odds are if you go on the internet and you type in pneumatic service unit, but you see it called FRL, for filter regulator lubricator. FR unit for, ours would be considered what we call an FR unit because it's a filter and a regulator. Ours don't have lubricators on it because all our valves are self-lubricated. The first one at the top, this is what we call a simplified, because this is the actual symbol. Now notice on these, it goes between a long, a dot, a dash, a dot, a dash, a dot. Anytime you see that type of thing around something, it's in the same unit. A pilot valve is going to be little small dashes, but they're all going to be equally pilot operated, and they're going to be equally spaced in small dashes. See, this is going between what? Dot, dash, dot, dash, dot, dash. This indicates that everything's in the same unit. This is the symbol for a filter with a drain. This is the symbol for a pressure regulator. Of course, this is a symbol for a pressure gauge. This is a symbol for a lubricator. Now, our service unit would be the same all the way up to that very end. Our service unit does not have a lubricator. And our service unit has a on-off, right? So it's got a ball valve on it. Are we okay? Now this is the same thing. So this straight line indicates a what? That takes the place of this, right? Then of course the regulator, and then this is the gauge, and this little line right here would be the lubricator. So on ours it would be the same, but we would drop off the lubricator. And that's a lot easier for you to draw than what? This. That makes sense? Yes, no. So that's what we call the simplified symbol. And that's what y'all would draw. So I went back into the labs we've done so far, and I've added what we've added in the circuit. So anytime we see any diagrams past this, it should have this symbol without the dash, and then the disconnect, the E-stop disconnect. I've added that to the drawings. Another thing that they don't talk about right now, they don't talk about into the system, but we're going to start using this, is what we call flow control. So if we can control the flow, we can control the speed of actuation. Unfortunately, what we're doing is we're deliberately putting a resistance in the flow, right? So that means each time we go through a flow control, we're going to get a pressure drop. If you get a pressure drop, that means your cylinder is going to create less force. So when you start calculating force, you need to know your inlet. You need to know the inlet pressure to the actuator, right? Not the pressure in the system. So what you would do is you would have to subtract the pressure across the flow control valve from the pressure being applied. Is that all that makes sense?
Okay.
So let's say I've got 80 psi.
Yes.
And I've got a flow control valve that drops 20 psi. And what would be available at the actuator? 60 psi. Exactly. How did you come? Yeah,
I'm just trying to, you're saying that the service unit regulates.
Right, but it regulates it at its output. It has no idea. It's just like Alabama Power regulates their voltage. But is that the voltage you get to your house? So when you look at National Electrical Code, they talk about when they talk about 120 volts. But if you ever understood, that's 120 volts plus or minus 10%, because they cannot regulate the voltage at your house. Now, every time you put current through anything, you're going to lose pressure. through the lines, through the transformers, you're gonna lose pressure. Well, how much work you get to your house depends on how much voltage you have at your house, right? You understand? So when we talk about how much force we can generate with a cylinder, it is how much pressure you have at the cylinder. And that's minus the losses in the system to get there. So anytime you go through a pipe, you're going to have pressure loss.
Okay, that's what I'm trying to ask. When you put 60 PSI, that's the pressure for the whole system.
For the regulator.
All the way to the regulator.
No.
To the exhaust.
No. 60 PSI is the pressure at the source. It is not the pressure at the cylinder. And some of y'all actually saw that, right? You understand that? Or at the actuator. Because when you start running this flow through a pipe, as soon as you run flow through a pipe, the sides of the pipe gives you opposition. If you have opposition in any system, you lose pressure. Right? You understand? So if we go to a flow control valve always do what? They lower the pressure. So when they start talking about speeds and all that kind of stuff, this is why in a fluid power system, so hydraulic systems, if we use oils are pretty neat in that they're self-lubricating. Air though and stuff like that, when they move, we're going to have pressure loss in the line. So our system we probably have a pretty good deal of pressure loss. In fact, some of y'all have so much pressure loss that the motor wouldn't even run, right? Well, if you look at our piping and everything, it's very, very small. We got like an 8-inch pipe that we're trying to run from the manifold into our system. Even though both pneumatic and hydraulic utilize fluid control, the textbook does not cover the topic of pneumatic in chapters. However, it's covered in chapter 10. An actuator area and fluid pressure determines the force. The power source flow rate determines the rate of the speed. The flow rate is determined by the pressure and the opposition to the system. Right? So what happens is that when we try to flow through something, we basically we have a pressure loss, and we have a reduced. That's what sets the flow, is how much loss you have in the system. Does all that make sense? So if I was going to try to figure out the speed of a cylinder, I would have to know the flow rate at the cylinder. I would have to know the pressure at the cylinder, right? Y'all understand that? So as soon as you come up and you put a T in the system, what happens to the flow rate? Huh? Well, it splits, right? You understand? So if you've got, 10 cubic feet per minute, and you run it to this actuator requires 5, and this actuator, and you split it, and literally, if the two actuators, you only get 5 and 5 out one, right? You understand? And that would also be true with a manifold. So we talked about meter in, meter out. Everybody understand these? So meter in regulates the flow of the inlet pressure side of the actuator. Meter out regulates the flow on the outlet side of the actuator. And then we have what we call bleed off. This is pretty popular in fluid and hydraulic systems, where they actually have a valve that bleeds off the excess pressure and just returns it back to time. Or flow, I'm sorry. So this is our symbol for a flow control valve. So we draw our line, and then we put these two concave semicircles on there. These would be a fixed, so on the left, this would be a fixed flow control valve. On the right would be what? Adjustment. Manually adjusted. So this is what we got over there. That we have what we call a one-way flow. And we're not going to look at these. These all came out of another book. So this is hydraulic. How do I know it's hydraulic? The triangles are colored in. These are a unidirectional pump, because if it's a bidirectional pump, it would have the arrows coming out of both sides. What do you think this is a symbol for? Anybody know? Tank, good. This is a flow, this is our actuator. This is the exhaust going back, well, this is the return going back to tank. This right here would be an example of what? Meter in or meter out. Now this would be meter in. This would be an example of what? No, this is still, yeah, meter in. Are we okay? Yes or no? Meter in affects the leakage. And we talked about the problem we have with meter in. I'm not sure what this is. This is the pressure release valve. We use the pressure relief valve in hydraulics a lot to set the pressure. So instead of running it through a pressure regulator, it works the same purpose, because anything above the pressure is going to be vented back to what? Back to tank. Now I don't know what we're talking about here. Like I said, this is not in your book. I don't know what that is. This would be an example of, it's variable, but it would be an example of, here's our pump here. This would be an example of what? Meter out, right? Okay. Okay, does that make sense? Let's see if it's got any more stuff in there. And this is bleed off. So like I said, this is very popular in hydraulic systems, where they actually take some of the flow and deliberately divert it back to where? Tank. And then they control the flow of what's going back to tank, and then your actuator gets what this is called bleed off. But you don't see this much in pneumatics, but you see it in hydraulics. And then we'll look here in a minute on something called a, now what advantage does meter out have over meter in? Yeah, the problem we have with, one of the problems we have with meter in is that when we come in here and we have this situation like this. Unless I'm coming over using meter in. And it could be a variable, it doesn't make a difference. This is what we call a negative load. So a negative load means load, the load. So what we have here is that even in a liquid, even with the hydraulics, that your load is trying to pull, even though liquids are non-compressible, your load is trying to pull that piston down. So if you got any leak in your system while this thing's trying to create this pressure pulling in, it's trying to suck that liquid out, right? So what happens if you got any leak in your system, what's it going to do? It's going to pull bubbles. It's going to pull bubbles into the system. The problem we have with pneumatics is that it's going to underpressure. So what would happen if we use meter in on pneumatics? The thing would stop. Okay, you know what I'm saying? We could push it up, but as soon as we got it up there, we turned that off and started exhausting this guy. It just off. The So what would happen to the gas? It would just uncompress, right? Another thing we have with, a problem we have with meter out in pneumatics is that what's happened is, as soon as we flow, it wants to uncompress anyway. So pneumatics are spongy, hydraulics is not. So if I want to control something precisely, then we're going to use hydraulics. Because it's not going to expand, it's not going to contract, it's going to move with the flow, it's going to do everything you can expect. Pneumatics, though, as we come up here and it moves, it kind of uncompresses, it hits the back of the piston, then it's going to have to recompress. The piston moves, it's going to uncompress, it's got to recompress, it's got to, so pneumatic cylinders are, if we use meter in, they're very jerky. Because they don't have a back pressure. They be jerky. So pneumatics have a tendency to be jerky, especially if we meter in. A single acting cylinder, we got no option, by the way. On a single acting cylinder, the only option you got is to meter in. Period. The only option you got is to meter in. Okay. Huh? On a single acting cylinder, the only option you got is to meter in. Okay? Y'all understand that? A double acting cylinder where it really comes into play. So what we do on a double acting cylinder though when we're in is we'll come up here and we'll do it like this. So what we'll do is we'll take both sides, and I need to get more room. Let me stop this and insert it. That's why I'm working on that right there. So on a double acting cylinder, we got two ways we can hook it up. So what we use is we use what we call a one-way flow control valve. So what these things are, they're literally a check valve and I should have drawn this first. It's a check valve in parallel with a flow control, with a flow control valve. And I think we looked at this the other night, right? Yeah, and I'm going to make it bearable because this is what we got. Just meter in or meter out? No. Not. So let's say we're trying to extend the cylinder. Let's follow the flow. So here I'm going to extend the cylinder. So here we come over here. Okay, so it hits the flow control valve. So one way it's got almost no opposition. The flow control valve, it's got opposition. So what's going to happen is your flow is going to go this way. It's going to unseat the valve, the check valve. It's going to come over here and it's going to push the cylinder out. No. Now watch what happens here. Okay, over here, now it can't go that way. Why can't it go that way?
It didn't meet it in because
it bypassed. Yeah. So, are we metering the inlet or are we metering the exhaust? Okay, so this is what? This is meter out. Now, why do we want to meter out pneumatics? Well, what happens is you constantly got back pressure. So what we've got is kind of like that spring on a single acting cylinder, except here we constantly got back pressure. So I'm coming over here pushing, but now instead of pushing against nothing, I'm pushing against something, right? You understand? I'm pushing against whatever that flow control valve is setting up. So if we have this flow control valve set at a flow that impedes 30 psi, and I've got 80 psi on my cylinder, then that's only 60 psi force, and the thing's going to move slower, right? You understand that? So we can hook them two ways. I mean, and it's real easy to look and see because all you got to do is look at the error on the check valve. So if I come over and turn the error this way, oops, as soon as I draw these right, guys, I'm sorry. So I should start up drawing my straight line first, and then do my flow control first, right? And what I'm going to do here is I'm going to point the arrow towards them. Yeah. So it's real easy to see. So if these arrows point toward the cylinder, it's what? Meter in. If they point away from the cylinder, it's meter out. Oops, I'm erasing too much. It's erasing too much. It won't take long. So let's go the other way. Let's retract it. So here comes my flow. Okay, it's going to go this way, right, through the check valve. Then it's going to come up. It's going to push it this way. Here it can't go through the check valve, so we're metering out, right? Understand? Now on this one, if I want to extend it, it's got to go through the check valve. Then it's going to bypass on the exhaust. So we're metering in. I could do the other side. So what we're saying is that all you have to do when you put those things in, and the symbol that's going to be on the side of the valve, there's very few of these things that don't put the symbol on the side of the flow control valve. So all you got to do, if you want to meter out, you point the arrows what? Away from the pipe, from the cylinder. If you want to meter in, you point the arrows on the check valve towards. So what happens is my pneumatic cylinder is always working against the back pressure. So instead of the thing jumping, it's going to get a lot smoother motion on that. But you got to remember, when you add those flow control valves on there, you're losing pressure. Which means that's something you got to consider if you're going to use flow control when you're calculating how big your cylinder needs to be to move to generate a certain force. And then you go out and say, well, I need a 4-inch cylinder to do 5,000 pounds, and you put a flow control valve and drop 40 pounds there, 40 psi there, then your cylinder don't move anything because you said, okay, right? You didn't think about what? You didn't think about the loss in the system or the loss in the flow control valve. So the higher to make the pressure, the faster you have the flow, the faster the flow. So when we say the flow determines the rate, that's true, but the flow is determined by the pressure in the system and the opposition in the system. That's what determines the flow, right? You know what I'm saying? So when they start talking about pneumatic cylinders, what determines how fast it's going to move? Well, if you don't have any weight on the dang thing, it's going to move faster. If you put more weight on it, then it's going to require more. It's going to require more pressure, which means the flow. It's going to cause the flow to do what? To go down. So it's hard to calculate the speed, especially on pneumatics. Really hard. We can get a sort of a ballpark. So the best thing to do is to get out there and use a stopwatch and do what? Yeah, time it with the load it's going to run. Just time it. It's still going to be up. It's still not going to be exact. It'll be close enough. If we wanted to be exact speed, we'd go away from these digital valves. Off and on, we'd use proportional valves. We'd add feedback from the cylinder, so the cylinder would say, hey, I'm going this fast. And then the system would take care of that. So unfortunately, we don't have time in this class to be proportional controls. they have them out there. So proportional controls is not extending the cylinder, retracting the cylinder. It's the cylinder telling you where I'm at and also what speed I'm traveling, which we're getting that in cars now too. Cruise control have been doing that for a long time. You know, when you go, so that's proportional control. You go at a certain speed, you engage your cruise control, and what does it try to do? Yeah, so if your car tries to slow down, it automatically does what? Speed up. Motorcycles, we had a throttle lock. That's what I had on my motorcycle, a throttle lock. So you lock the throttle. It run real good on what? Straightaway, but as soon as you go up a hill, your bike will slow down, and you go on the other side, you'll be going 90 miles an hour. I think some Gold Wings and some of the big bikes have true cruise controls on it, but regular motorcycles. Okay, any questions on that? Okay, guys, y'all take a break. And then we'll get back into actuators. 10 minutes, right?